Hello everyone and welcome to The Public Space. Today we talk about space-time, an undeniable concept since it's present in every physical equations that exist. It determines the distance between us, determines the way we are impacted by gravity, by electricity. But does Bill Gates differ? We'll ask him tonight. Hello Bill, how are you doing?
How you doing, Jeff? How you doing?
I'm doing good. As a reminder to our crowd, you can join us on Entropy if you have questions for us tonight. The survey of the night is, do you agree with Bill about space-time? So we'll see what he thinks of it. He tends to be a subversive scientist. He tends to be questioning the concepts. What about space-time, Bill? Does it exist?
Well, in order to know whether space-time God or a leprechaun exists, we have to define the word exist. And the word exist has never been defined in the last 10,000 years, as far as I'm concerned. You look it up, and what you find is a synonym. You find being, you find to be, you find living, you find reality, you find all these synonyms. And when you look up those words, they just say exist. So we don't have a definition today, and you don't have to take my word for it. You can go to the Stanford Encyclopedia of Philosophy. You can go to the Internet Encyclopedia of Philosophy. You can go to any of these, and you won't find a definition. What you will find is what all the philosophers throughout history said about exist. And today we don't have a solid definition anywhere. I define exist very precisely, very concisely. And I'm saying that rigorously, right? That you can use it consistently, scientifically, rationally. And I define it saying that it's an object that has location. The synthesis for the definition is physical presence. That means an object that has location. If God wants to exist, if space-time wants to exist, all it's got to do is be an object first, a physical object, a thing, and then it's got to have distance between God's chest and my chest. In other words, he's got to have location. And I don't care if God wants to hide in the 26th dimension, there should be a straight line connecting his chest with my chest. And then he exists by definition, not because I believe or disbelieve.
So then it seems that space exists because location requires spatial coordinates, doesn't it?
Space is not a physical object. The first criterion for existence is it has to be an object. It can't be a concept. Love cannot be said to exist in physics, in science. Love can be said to exist in ordinary speech. We can say, oh, love exists, very poetic. It has no meaning in science. In science, only objects can be said to exist. And the way we figure this out, the best way to imagine this is let's kill all observers. Let's kill all life in the universe. What remains is what exists.
All right. So let's get started on this train. So you have brought us a couple of pictures to illustrate the concept. What happens if we start considering space-time as something that doesn't exist, but that is a concept? I mean, I don't take issue with this. It's just a special definition of exist. Where does that bring us?
It brings us to the point where mathematical physics has, at least since the 17th century scientific revolution, has gone more into concepts and less into objects. Physics is about objects. Physics cannot be done without an object. You have to have a thing. For that, you have to define what an object is, what a thing is. And what mathematical physics has taken science, they went on a tangent. It took us along a road that leads us to introduce concepts as physical objects. You'll hear a statement or a phrase such as transfer of energy, moving a mass, bending of time, stretching a field. And there are no such physical objects. Those are all mathematical concepts. And not only have we brought these concepts into science as physical objects, but now we say further that they exist. Because, they say, well, does a magnet have a magnetic field? Well, what is a field? Well, they don't worry about that. It's a mathematical concept. But suddenly the field is not only a physical object, but it also exists. and we have to get into the language at this point because these people are essentially introducing objects, concepts as physical objects, and then compelling them to exist. And that's the physical interpretations that we are receiving.
Okay, well, we can categorize the world in objects and concepts, but that being said, there is such a thing as the differential effect of gravity based on distance. You agree with this, right?
Oh, totally. Newtonian law equation I bow down to.
So the gravity, okay, it doesn't exist as an object, but it exists as a relation between two things that are distantly separated.
Okay, I'll agree with that, but I'll go further and I'll say that it's not only a relation, because that would be a mathematical perspective. I'm going to say from a physical perspective, there had better be something, an unseen, intangible object that serves as mediator, that causes gravity. And that's what a physicist has to figure out. What is it that produces gravity? What causes gravity? There has to be a physical object, or otherwise we're introducing spirits in there.
All right, so let's get started on the images. You introduced the concept of simultaneity in this train example. What do we see here?
Well, this is how special relativity began at the beginning of the 20th century. Essentially, not only Einstein, but even other people, like him, Minkowski and others, they came up with this notion of relativity, saying that they put the observer at the center of the action, and they said it's what the observer perceives. And in this case, what we see is a train. It's being hit in the front side by a lightning bolt, and also in the back. If the lightning bolt hits front and back at the same time, a person that's standing in the like that one there, standing in the platform, will see those two lightning bolts hit at the same time because he's equidistant from both front and back of the train. However, a passenger on the train would see it differently, would have the front side of the lightning bolt hit the front side, get to his eyes faster than one in the back side because he's moving in the direction of the lightning bolt. And so what Einstein was saying with this, and others as well, is that it's all relative. It's this simultaneity that the observer on the platform observes. That's a question of relativity, because the person who's moving on the train sees something different and therefore measures something different. Okay, and so from this they extrapolated that some of these variables are not. Some are variables and some are not variables. For example, what Einstein came up with is that light travels at a fixed speed, independent of the movement of the observer or of the source. But then each individual measures then the other factors as variables. Time, right? Time is what becomes a variable, and distance. Those become variables. And Absolutely. From there, they extrapolated later to general relativity. They generalized the theory, and eventually we end up with this concept known as spacetime, which is essentially a four-coordinate system, as they call it. And I'm saying it's not even coordinate or dimensions or vectors. It has nothing to do with dimensions, coordinates, and vectors of physics. It only has to do with number lines.
Yes, it is a number line, the space-time, and the space-time can be bent, which is the only way we can reconcile, I guess, these different observers seeing different things from the universe. You have to think that the train gets smaller as it advances faster, and that time bends also.
Yeah, but one interesting part of that is that the train, according to Einstein, right, and mathematical physics still stands behind that, the train cannot travel exactly at the speed of light. You don't want to convert all that mass into just energy, And so the issue is that's an equation, and they don't want that zero in an equation, where the train goes so fast that you have velocity of light over velocity of light, essentially, a one. So the train can only travel slightly less than the velocity of light, and therefore it can shrink as much as you want, right? But never down to zero. And the question is, why didn't they go to that zero? Because that means the train disappears if it can travel at the speed of light, which means that now how do we get it back if it disappeared? So it's I think it's ad hoc to say that we cannot travel at the speed of light, and that's only a mathematical. That's only an equation. Okay.
Now it does seem that
there's no reason to say that something cannot travel at the speed of light, other than the fact that it goes completely into energy and that it shrinks completely to zero volume. And then now how do we get it back?
Yeah, that being said, do you recognize, for example, that there is an increasing amount of energy to increase your speed as you approach the speed of light?
Yeah. But again, those are mathematical concepts. Keep that in mind. All we're saying is we have used the word energy, the word mass, the word time to designate certain concepts, and they make sense in mathematics. The problem is now interpreting that from a physical point of view. That's where I come in. I'm saying that none of these people are giving us rational explanations for their equations. So I'm not disagreeing with the equations. I have no problem with the equations because I'm not interested in that. I want them to tell me how the universe works. I want to know how gravity works. I want to know how magnetism works. And they cannot come to me and say, look, the way gravity works, the reason the Earth doesn't fly out of the solar system is there's a depression created by the sun in space-time. They cannot tell me that because space-time is not a physical object. It's a mathematical concept. It cannot serve as a wall to the exit or to the leaving of our planet out of the solar system. It cannot block the escape of the Earth because it's a concept. So the physical interpretation that Einstein gives to his equation, that's where we have a little bit of a difference.
All right. Now you have an illustration of the concept of simultaneity, a little bit like the case of the lightning bolts on the train. But what are we seeing here?
Well, what I'm saying is, let's look at objectivity versus subjectivity, mathematical subjectivity versus physical objectivity. If we place Einstein in a electric chair, right, equidistant from the 2 points, right, and we have on a railroad track, and we have a train running through the railroad track. As soon as it touches the front wheel and the back wheel touch simultaneously, the wires connecting to the railroad track to Einstein, to his electric chair, he should be fried if he gets the 2 bolts at the same time. If, on the other hand, one bolt hits Einstein before the other one, he doesn't get fried. And the question is, does Einstein get fried or not? And I'm saying physics says that he will be fried, because we don't care about interpretations. We care about the physics. And the physics means that if the front wheel and the back wheel touch exactly at the same time, not as measured by anyone, just physically, they touch at the same time, both bolts will reach the electric chair, and there will be enough voltage to fry Einstein. If, on the other hand, the front wheel reaches before the back wheel, then obviously he will not be fried because there's not enough voltage. And that's a physical issue, not an observer-related, opinionated issue.
Are you saying that these statements are at odds with general relativity?
The physical interpretation is. The physical interpretation of saying, well, what the observer measure, what did the observer see, what did he perceive? That doesn't enter the picture of physics. That's subjective. We're not interested in subjectivity. In physics, we're interested in objectivity, complete objectivity. For that, we remove the observer, we remove the mathematician, and say what exists out there independent of the observer. And
but again, what is it that you take issue with here? Because it seems that The train will pass. It will send the electric shock if it's properly configured to do so. The electric shock will arrive to Einstein. It will be a wave of electricity starting from the negative side to the positive. What is the problem here? Are you saying that there's a problem with the spatial contraction of general relativity?
No, I'm saying that the issue of introducing an observer, a measurer, a person who's going to do measurement, and how he perceives light, electricity, or whatever, it doesn't enter the picture in science. In science, we're not interested in what the observer perceives or measures. What we're saying is, if we were to figure out what the word simultaneous means from the perspective of physics, as opposed to the perspective of mathematics, equations, what we're saying here is, if the two lightning bolts arrive at the chair simultaneously, physically, the guy will be fried. And if they don't, he won't be fried. And that's not what mathematics says. Mathematics says, well, this observer saw it this way and the other guy saw it that way. The guy on the platform saw him coming at the same time, and the guy on the train saw one come before the other. That's not the case in physics. In physics, it's one or the other. They can't have it both ways. And that's why this issue of relativity, of how each one measured and perceived the event, plays no part whatsoever. And that's what the mathematicians did for the entire 20th century. They introduced the observers and measurement.
I mean, I will take some issues with this because it seems to me that there is an observer here. It's Einstein. His observation is whether he is receiving enough electricity to be fried. But what general relativity tells us is if this was happening at extremely high speed, which of course will not be reachable by a coal-powered train like this one, but suppose that the train was going close to the speed of light, the person on the train would not see the same sequence of events leading to the explosion of Einstein, but Einstein would see it.
But the question is whether the observer on the train or the one on the platform, what they perceive, what they see, what they measure, what does that have to do with the fact that two lightning bolts either hit simultaneously and fry the guy, or one bolt comes before the other and they don't fry the guy? It's a black or white issue. If Einstein dies or gets carbonized, like I show there, then they hit at the same time. And if he doesn't get carbonized, they didn't hit at the same time, period. We don't need the opinions or perspectives or measurements of observers.
Okay, let's move on. I'm not sure about this, but let's move on to the third PowerPoint.
Okay, just to show you there that this is, people sometimes expect authority. Well, here you have a lot of authority. You have Steven Weinberg, he's a Nobel Prize. He says, I don't think mathematics can ever be regarded as an explanation in itself for anything. And this has not always been well understood. In other words, mathematics can only describe. Mathematics has no power to explain. And people don't always understand that. They think that we have explanations today, and we don't. We have irrational explanations for common phenomena. And then when you go and try to talk to the mathematicians, try to present a paper, for example, I've submitted papers to Science and to Nature, and they were rejected because they say these are philosophical issues. They think that speculating about how the universe actually works is not a concern of physics. They're only interested in the mathematical description. And so people don't always understand that. When you go to Donald Simonek, a professor emeritus at Lock Haven University, he says science doesn't explain, science describes. So the notion that people have that physics is about explaining, they say this, but it's all lip service. There is no explanation, no rational explanation. When you confront the mathematicians like I have in the past, they say, oh, but you're looking for causes and for mechanism. Yeah, I said, yeah, that's what I'm looking for. They said, well, that's not physics. That's not science. That's philosophy. And so we got a problem because I'm interested in a physical interpretation. I want to know how a magnet works. And they're saying that that's not part of physics.
Yeah, definitely you are on a path of mechanistic explanation of the physics that we know of. Yes. So Stephen Hawking, was he on that path too? He wanted to understand how the world works.
Yeah, but apparently they are not concerned because you get other statements that I don't know if I've sent them to you, but people who say we can't understand this universe. There's no way we're going to understand it. Science is about researching, about trying to study the universe, but never finding, never discovering. In other words, science is a process of discovery and never one where you reach a dead end and say, okay, now I can explain how the universe works. They don't think in those terms. They think it's an ongoing process, and obviously it does create job security.
Yes, as the humorist in Quebec was saying, his name was Saul. He was saying, as long as we pay them for researching, they have no interest in finding.
I love that. Yeah. Give them a medal. Yeah, it's true. I mean, these people are only interested in equations, in describing. And here you have two gurus who are telling you, we don't explain, we describe. And people don't yet understand that. They think that we do understand how the universe works, in part because of the fact that we have technology. And they say, well, the technology proves the theory. And that's not true. That's where the connection is absolutely false. The fact that a computer works does not prove that quantum is right. The fact that GPS works does not prove general relativity or special relativity. It doesn't prove that you can bend time, which is the explanation that these people give you. And so the physical interpretation is irrational, but most people out there, at least people who don't look at it deeply enough, they think that because we have GPS, that's proof that special relativity is correct. But what they're saying essentially is that, if we go by this, what the mathematicians are saying is we can bend time, we can stretch time, bend it, do all kinds of things with time. That's how that's the physical interpretation. That is the theory. And and the other part is a description, just a mathematical description.
Now, it seems to me that description is something. It is knowledge. Would you agree with this?
We frown on the word knowledge. There is no such thing as knowledge. So all these words have to be defined because people introduce the word exist, the word knowledge, the word, all these words are introduced and people think they know what they're talking about. Knowledge, I define it a little differently than all these other people. I define knowledge as the ability to predict the outcome of an experiment without error. And there's no such thing. Not even God can do that.
Without error? That's how you increase your threshold? Yeah, but
I'll give you an example so can put it in the right context. Let's assume I drop a pen 10 times and 10 times it falls to the floor. So now I'm going to prove my knowledge to you. I say, okay, JF, I'll bet you $1 million that when I let go of my pen now, it's going to fall to the floor, right to the center of the earth, right? And it turns out I let go of the pen and it stays in the air, and I lost $1 million to JF Gaede. Yeah. And I said, what the hell happened here? And it turns out that you tricked me. You either had some air pushing the air from below, from the pen from below, or you had a couple magnets on the side holding the pen in the air. You tricked me. So I did not know that the pen was going to fall to the floor. I was guessing. I had an intelligent guess based on my experience, but I did not know for a fact that the pen was going to fall to the floor, let alone that an asteroid comes and destroys the Earth and neither one of us collects on the bet.
Well, it seems that our differences on the definition of knowledge is absolute and perfect versus incomplete. I recognize the value of incomplete knowledge. For example, if I have a coin and it gives heads and tails, but it gives heads, let's say 60% of the time, I could say this coin is loaded, and that is knowledge to me, even if I can't say on a specific drop whether it will drop on the head or the tail. I have some knowledge of it to me.
Unless someone is tricking you, maybe God, maybe one of your buddies, and he's using magnets to do some funny thing in there, and then it's not that the coin is loaded, but that there's some other phenomenon going on that you're not aware of. And again, how knowledge is defined today is we still have the definition of Mr. Plato, and that's justified through belief. And when you come to think of it, we all know that God exists, don't we? And there's a lot of people out there who know that God doesn't exist. And so the question is, who knows?
All right. Let's get to the Leonard Susskind quote. What
Yeah,
is that
here's
about?
this mathematics, and I don't try to see it in my head. And trying to explain it to people who don't have mathematical background, we get stuck. I can't say, now close your eyes and view in your head 5 dimensions, because I can't do it either. All I can do is say, take X, Y, and Z and add V and W. Eventually, a person with this type of mathematical background begins to develop mathematical intuitions for things. They don't need the same kind of visualizations. So we're stuck needing mathematics because evolution didn't equip us to be able to visualize quantum mechanics. It didn't equip us to visualize 11-dimensional space-times. Evolution did this to us.
Makes sense to me, doesn't it?
Well, what he's saying is we're 3-dimensional beings stuck in a 3-dimensional world with which we are familiar with, right? And the issue is there a 4-dimensional, 5, 6, 7, 10, 26-dimensional universe out there? And we cannot see it because we're stuck in 3 dimensions, like a 2-dimensional flat that lander would be stuck in flatland, right? He would not be able to relate to a 3-dimensional solid land world. And, they use that analogy to say why we cannot imagine the 4th dimension or the 4-dimensional world. But when you look at what do you mean by 4-dimensional, what is this space-time, 4D space-time? And when you look at it in more detail, you find out that they're just 4 number lines that they use to locate a point within space-time. So it's like a circular argument. What is space-time? Space-time is an event that can be located with 4 number lines, right? Because they're not even coordinates within space-time. That's what space-time is.
Absolutely.
So what meaning does that have in physics? I mean, in mathematics, yeah, it might have all, they want to locate a point and label it and tell me how many coordinates they can precisely pinpoint it within space-time. They can do whatever they want, but they can't later on extrapolate that and say, okay, I'm going to bend space-time, and that's how I'm going to produce gravity. Partly because of one of the other things I sent you there, you need a force to bend space-time. For that, you need to, it would be number, it's number, what is this, 18. You look at number 18. See, you got to push it down. You got to push the Earth down on the canvas, right? And then the question is, why doesn't the Earth push it upwards? See, if they showed this, what comes next? If they showed that, people would say, oh, that's counterintuitive. What do you mean the Earth pushes space-time upwards? So they always have, the Earth pushing the fishnet downwards. That's the physical interpretation they offer. And that's misleading because space-time should not have any direction, in any
That's very interesting. I had never realized this, but the idea of stretching in general relativity is always one directional. It's always stretching down rather than stretching up. We don't have such a thing as positively spaced curvature.
But the reason for that, let me just address the first part. The reason for that is that gravity is one directional. Gravity is always towards the other object. The moon is attracted towards the Earth and the Earth towards the moon. In other words, they're going in one direction. And so you have to explain that direction. If gravity were multi-directional, we wouldn't have this issue with a fishnet. And yeah, I think there's a serious problem with that because you need force to explain that pushing down on the fishnet if you're going to give a physical interpretation. And again, if you're pushing down a concept, I don't even know why the fishnet represents that concept called space-time. What you have is a 3-dimensional what you have is a 3-dimensional fishnet shown in a 2-dimensional image. And they say, well, we cannot imagine it in 4 dimensions. But anyway, you look at it, it's a concept. What is space-time? Time is a concept. Are you going to take a 3-dimensional rock, put it together with 5 seconds and create a rock time? What is that? What kind of object is that? What sense does that make?
Now you send us a tesseract. This is mind-boggling.
See, that's supposed to be 4-dimensional according to them. What are we looking at? Well, what we're looking at is a box within another box. That's objectively what's in front of our eyes. And what they do, they put it in motion to incorporate time within that image. So what we're looking at is a photograph of a movie. That's what space-time is, a photograph of a movie. What you're seeing is a box through time expanding, and that's what they call space-time. In other words, space-time is a dynamic concept. It's not even a static concept. You can't talk about a four-dimensional tesseract if a tesseract is supposed to in some way represent space-time. It's a dynamic concept.
I'm not sure what is being illustrated here. What I see is kind of a cube just moving into another cube and extending its borders. Is that a four-dimensional space representation?
It's supposed to represent the four-dimensional space. They're trying to present it so that people try to understand more or less what they're referring to. And what they're saying, a tesseract is actually a box that is expanding through time. And it's a big problem because it means that this box is built with time, with something which is dynamic. Okay, so you can't really see a tesseract in one piece because all you would see is a box inside another box. It would be a three-dimensional image planted onto a two-dimensional platform.
All right. Personally, my favorite way of visualizing 4D space, although it never led to anything productive in my head, I imagine slices of 3D space. I imagine a cube at t equals 0, and then a cube at t equals 1, and then a cube at t equals 4.
More or less. Yeah, I don't know. It's a concept again, and if you look at some of these other which one is it? Yeah, look at number 10 there. This shows you how these people are doing. What they're doing is they're saying that mass warps time. Space-time is that little fishnet there. It's supposed to be a four-dimensional fishnet of some kind, 3 dimensions of space plus 1 of time. Okay, let's even concede that for the sake of argument. How can mass, a concept, how can kilograms weigh and bend space-time? What are we talking about? What does this have to do with physics?
I think we don't know why. But I think it has been measured that there is a gravitational effect on the warping of space and time. Am I wrong on this?
Well, that's their physical interpretation. But again, it comes back to the wording. I mean, what do we mean when we say that we bend time? Forget about space. Okay, we'll concede space. Let's say space is a physical object. Fine. How can we say that we bend time? How can you bend the concept? What are they bending? A second, a minute, an hour? Maybe it's a calendar. Maybe it's a year that they're bending. What are they bending? In other words,
what I'm trying to say, for whatever reason,
we cannot understand their physical interpretation because their physical interpretation is not physical. It's concepts that they're bending. They're saying we're bending love. If I told you gravity is the bending of love, you would say, well, I didn't understand it. What do you mean the bending of love? And
well,
this
it would mean that if I'm close to a highly... It would mean that if I'm close to a highly gravitational field, the woman will take more time to be ready for sex. You can bend a concept in that you can make it evolve faster or slower. In the case of the bending of time, what is the claim is that an observer that is not subject to the gravitational field versus one that is subject to the gravitational field, they will have perceived a flow into the future that is either slower or faster.
That's a mathematical description, a perfect mathematical description. We have no problem with that, and we don't care about that. We want to know what the physical interpretation is of that you just said. Why?
Well,
what causes it? What's the mechanism? That's where we have a problem.
We do. We don't know that. I tend to think that we're kind of in an elevator advancing toward the future. I like to think of the universe as a box that is advancing at the speed of light into the dimension that time is. But I have no idea if that is correct.
It's not correct because time is not a dimension. Dimension is length, width, and height. That's a dimension. Time has no relation whatsoever to length, width, and height. And what they're saying is space is length, width, and height. And then we have time. And even Stephen Hawking would say that there's no difference between a time and a one of these regular dimensions. Why? Because they don't care. They're only looking at numbers, and for them, they're all number lines. What they've done is confuse the dimensions of physics, length, width, and height, with the number lines of mathematics, which has no direction and has magnitude. And length, width, and height are the opposite. They don't have magnitude, and they do have not only direction but orthogonality. So there's a big difference between them. The last number, what is it? Number 20. Synthesizes the difference between dimensions of physics and those of mathematics. See, a dimension is length, width, and height. A box. That's what we say. It's three-dimensional. That's why we call it three-dimensional. To say that something is four-dimensional and by incorporating time, all you're doing is saying that the box is moving. And so does the tiger become four-dimensional because it moves through time? What are we saying here? Are we talking about a four-dimensional object, or are we saying that a three-dimensional object is moving through time? These are different things. And coordinates are different than the number lines of mathematics as well, and so are vectors. Vector is a dynamic concept. We have depth, breadth, and elevation. Those are the names of the vectors in physics. In mathematics, they don't use that. They don't have any use for qualitative dimensions, vectors, and coordinates. What they use is number lines. That's all they use. And number line has one thing that is specific to number lines and to math, and that is it has no direction. Time has no direction. What it has is magnitude, and that's where these things differ. One is qualitative, the other one is quantitative.
So the classical physical answer to these differences between the spatial dimension and the time dimension is to give a special property to the time dimension. It behaves differently, the time dimension, than the space dimensions. But in your setting, how do you define time? How do you understand time?
Time we define as a comparison of two motions. You have to have a memory device. You have to have a recording device, memory. You have to memorize the motion of one compared against the motion of another object. So the difference between motion and time, that's the first distinction we have to make. Motion is an object that occupies at least two locations, and time is a comparison of two motions. And you need a recording device. You need memory to conceptualize time. You cannot have time without memory.
All right, very interesting. You have sent us other images that was relating to the Einstein's predictions about gravity, and I think that you've already mentioned on a previous show that the verticality of the Oberon or Uranus, what was it? Its orbit was acting differently?
No, the issue is the following. We cannot extrapolate Einstein's equation to a three-body system. We can do it with a two-body system. We just have the sun weighs down the canvas of space-time. Let's concede that. And then the Earth rolls around that depression. Fine, no problem. And we can even do it with the moon. We say, okay, the sun weighs down the canvas of space-time, the Earth rolls around, and the Earth weighs its own canvas downwards, and the moon goes around the Earth. So far, so good. But what happens when we go to Uranus? Well, we have Oberon, and it doesn't, Uranus does not weigh the canvas downwards. Uranus pushes the canvas outwards for Oberon to go around the poles. And when you go to the system of Pluto and Charon, what you've got is the Charon moves towards the sun and away from the sun. In other words, it's going towards and away from the sun around Pluto. And so for that, Pluto would have to push the canvas sidewards in the direction of motion. And so, we don't have consistency between three-body systems in these three separate instances. In other words, the Earth with its moon, Uranus with its moon Oberon, and or any of its moons, and Pluto with its moon Charon. You don't have
That's
consistency.
fascinating. I didn't know that we had the three orthogonal positions for orbital interactions in bodies that rotate around the sun.
Yes, sir. You can look it up. Don't take my word for it.
So what is the takeaway from this? You have a better explanation than the
Yes,
bending of space-time?
I'll illustrate. Now, this is $1 million experiment. I hope you send me the check later on, okay? Here it is. Look how simple it is.
Okay.
Okay, so here's the Earth, and my hand will be the sun, okay? Think of it a ball here, right? So if we're attached to the sun, it's very simple to understand what I'm saying. The sun moves the Earth around because every atom on Earth is attached to every atom of the sun. And likewise, every atom of the moon is attached to every atom of the Earth. So it's like the epicycles that, what is it? What was his name? The Greek guy.
I don't know.
I lost
Ptolemy, Aristotle.
Ptolemy, sorry. Ptolemy.
Okay.
He wrote in his book, Almagest, he wrote about the epicycles, which is, think of it as a cowboy going around in circles with his horse, and at the same time, twirling a lasso over his head. That's essentially what each one of these looks like from my perspective. In other words, you have the cowboy attached to a center with a rope, and the rope, the lasso, is tied to his hand through another piece of rope. So one is twirling around the other, okay? And if we look at it that way, then if every atom in the universe is interconnected with all others, then we can understand gravity very easily because it's a pull mechanism. Now we have not something pushing the Earth towards the sun or a depression along, like a roulette where the Earth goes around the sun because there is a depression caused by the sun. Instead of that, what we have as a physical interpretation, we have every atom on Earth connected to every atom of the sun. Now we can understand how the sun twirls the Earth around itself and the Earth twirls the moon around itself.
That makes sense. It's the rope theory, but then how do we explain the orthogonality of certain satellites? Why is Oberon that way? Why is Charon that way?
Well, part of it is due to the spin of those planets. If you look at the spins, they are related to the direction in which the moons twirl. And when you look at the spins, then there's no mystery. Because now the sun twirls Pluto around in this direction, like it does with all the other planets, but Pluto twirls Charon in the direction of the sun, because that's the spin.
So it is the sense of rotation of the planet that determines then the satellite's direction?
I think in most cases, we got to look at each case individually. There are other factors working in each one of these cases. But in general, yes. In general, I would say that if you look at how the moons go around the planets, we have to look at, in general, at the spin of the planet.
All right. Bill Gaede, was this all for tonight, or did we have anything else to talk about?
No, the only thing I wanted to show that if you look at anything from 11 to 19, these are all the irrational mechanisms proposed by general relativity. Here you see, I put these walls there because that's the depression. And the question is, if there is a wall of space-time that blocks the escape of the Earth out of the solar system, if that's the mechanism, why does the moon go through that wall? And if you look at the next picture, the one about the comet, same thing. Why does the comet go through that same wall that prevents the Earth from moving out of the solar system? And you can say that also about astronauts and other, we sent the rover to Mars. And the question is, how did the rover get to Mars if there's this wall of space that prevents, the rover from prevents first the Earth from leaving the solar system, but it doesn't prevent the rover from going through that same wall. We have to explain that difference.
It seems to me the answer to your question is that they don't get trapped in that local area because there is, on top of this representation, there is an initial speed. The comet is coming into this hole at a certain speed that will allow it to escape it eventually.
Well, all I'm saying is I'm trying to illustrate the problem. The problem is that if the depression caused by the sun in space-time is what prevents the Earth from leaving the solar system, if that's the physical interpretation, then the question is, why can things go back and forth, into the sun, like in this case the comet, or why does the moon go through that same wall? I mean, we have to explain that difference. Why can the moon go through space-time and not the Earth? It's like if the Earth was a roulette ball, right? And the Earth cannot leave the roulette, right? Because you twirl it around and it's going around the depression. Well, why can the moon go into the roulette and back out? Why does it have its own roulette? You see what I'm saying?
Right. Yeah, I get what you're saying, but I don't think it's a problem because I think that ultimately it's the sum of influence. In other words, the moon is attracted to the sun on average, and it's essentially the pair of the moon and the Earth that's attracted to the sun, but this bending is not enough to keep the moon from being influenced by the depression of the Earth itself.
Well, what we're saying, we have a depression inside a depression. I guess that's what you're saying?
Yeah.
And we have a depression inside a depression. Why does the moon go through the depression of the sun? Because there should be a bigger wall caused by the sun than by the Earth. The Earth has a little depression, the sun has a big depression. And that's not counting all the other planets in between and beyond, right?
Well, not if we include the distance. The sun is very far.
But the sun can be very far, but we cannot leave the solar system according to general relativity because there's a wall of space-time that is bent right behind us. The skin of the planet, of our planet, is rubbing against this space-time that doesn't allow us to leave the solar system. That's the physical interpretation. And so this has to be a major wall. This is bigger than the Berlin Wall. You know what I'm saying here? And here you have this little moon going around a little depression of the Earth, and it's just going in through that sun's depression back out. It just goes around, just breaks through the wall and back out. You would think that the depression wall of the sun is much bigger than the depression wall caused by the Earth.
All right. Personally, I don't see it as a wall. I see it as a force, a tendency. The more you are into the depression, the stronger the force is. But it seems that the Earth is at a distant enough position from the sun to just have an equilibrium where it keeps its distance away from the sun in a stable fashion year after year. There's lots of reactions from the crowd. Tim K says, what will happen to ropes if the expansion of the universe exceeds the speed of light under some models of the future?
Well, we can't talk about the extension of the universe because the word universe is a concept. Universe is a concept that includes two, you can call them entities or words, concepts that are treated as entities. One is space and the other one is matter. Okay, so we have all these atoms in the so-called universe, and space is part of the word universe. So universe is equal to space and atoms. And to say that the universe expands or the universe does this or that, that's irrational. We have to say, what are we talking about? Are we talking about the atoms expanding, getting away from each other? Are we talking about the expansion of space, a concept which means exactly nothing, vacuum, emptiness? What is stretching? What is it that is expanding? Are we talking about the atoms or space?
All right. Howard Bill ask a question that is outside of your domain of specialty. He says, Bill, how did the Neanderthals disappear?
I wrote a book about that.
Oh, you did?
Yeah. There's how the Neanderthals disappeared. And
I was not aware of it.
Yeah. I go to see, they say that first the official version or the most popular version today. They intermarried with us. That's how they say we disappeared. They disappeared because they intermarried with us. What happened was supposedly we were a much larger population, and they intermarried with us, and slowly they whittled away, and we remained, and that's why we still have like 2 to 3% DNA belonging to Neanderthal in our blood. The first problem with that theory is that officially, from the record, okay, the Neanderthals have been shown to have disappeared 40,000 years ago. They can't find any more of their technology after 40,000 years, after visiting several of their sites in Europe, right? The first human skeleton that appears in Europe, which is in Romania, appears 35,000 years ago. So if we just go by objectively by the record, the Neanderthal disappeared 5,000 years before humans entered Europe. And that to me makes sense, because I think it was the Neanderthals that kept humans out of Europe. And it's when the Neanderthals disappeared that the humans could finally enter Europe. Now, how did they disappear? I'm saying all species disappear in a background extinction in 2 ways, essentially 2 mechanisms that create their extinction. And this happens to all species, plants and animals. And to us, it's happening right now. And that is, first, we lose our genetic diversity until there is none. We can't create new genetic diversity. We can only lose it. Okay, and that's a long story, but that's the first factor. The second factor is, at the end of or close to the end of a species' lifetime, the population pyramid overturns, and in other words, more individuals of that population grow older and fewer are younger until the whole pyramid overturns. And you can show that with a little piece of bread that you leave on the table overnight, or probably a little longer, and it turns green, and all these bacteria, they just multiply until they cover the whole world in which they live, which is that piece of bread. And then after that, it just decays until you get extinction.
Wonderful. So you can prove extinction. There was a news item on this. The National Post publishes, there used to be 9 species of human. What happened to them? The disappearance.
I saw that article the other day myself.
All right.
And again, I'm saying they disappear all by themselves. We didn't kill anybody. We didn't cause their extinction. No species causes the extinction of another. What happens is all species implode. They implode because their genetic diversity it disappears. It has to, unless it can create new environmental conditions. And that only happens at the beginning of a species' lifetime, when it branches out from the mother or the main branch, the main trunk, okay? So they encounter new conditions. That's when they create genetic diversity. Genetic diversity eventually whittles down through a series of thousands of years of bottlenecks and founder's effects. So you have a series of of bottlenecks where there's a disease or whatever that causes the lots to die. And from there, you have a founder's effect that now creates the next generation. We have this successively, and that streamlines the genetics of that species, unless it can mate with something else.
It's an interesting view. I think that you are highlighting very important processes of evolution that tend to be not necessarily discussed mainstream. That being said, I think you're a little too radical when you say species don't cause the extinction of other species. I mean, you can certainly make a scenario in which a species takes the ecology of another species and keeps it from exploiting it.
Well, yeah, you're saying competition. I don't think competition has anything at all to do with extinction. Neither competition, neither climate change, none of those things have any effect on species. It's just that in this day and age, we have all these things like climate change, which are so deep in our hearts and in the news and everything, and everybody says, oh, climate change. I say it's got nothing at all to do with extinction. Extinction comes when genetic diversity disappears and the population pyramid overturns.
Very interesting. Zurpater says, light, fire, electricity, magnetic attraction, are these physical objects that exist according to Bill's definition of existence? Are ropes physical objects that exist?
Good question. Good question. Atoms, we can say exist because we can say they have they're objects and they have location. And every time we always use the word location, we refer to objects that we could see and touch and feel, etc. We can't touch the rope. We cannot. Mother Nature was wise in her, or God, or whoever created this, right? Was very wise because they made the rope intangible and unseeable. Okay, so we cannot see or touch the rope. Therefore, we cannot prove the existence of the rope by going to the lab and say, let me run an experiment to see if the rope exists. No, you have to sit back and define the word exist first and then conceptualize. That's the way to reach this problem. And of course, if you go out there and say, well, how am I going to define the word exist? Well, I'm going to define it as a physical object. Okay, it's got to be an object, and then it's got to have location. And the question is, does the rope have location? And the problem there is that we've always measured or conceptualized location only between atoms, between things. We never conceptualize it between that which we could not see. So if you see two atoms and you can't see the rope between it, you can't touch it, as far as you're concerned, there's empty space there. And no, under the rope model, distance is length, the length of a rope between two atoms. So we don't have empty space or space between two atoms. What we have is a rope. And if we're going to limit the word location to atoms and above, then the rope under that definition does not exist. Other than that, it's an object. And again, the bottom, the ultimate hypothesis, there's a single thread in the entire universe that converts into atoms and ropes, atoms, ropes, atoms, ropes. It's a single thread if we could untie it all completely. And again, does the thread exist? Well, for that, it would have to have location. Location with respect to what? And again, it's a question of definitions.
Quote of the night, you can't touch the rope. Neutrinoid Fractalite says, what is the difference of using math or words in a sentence? What makes one better than the other? Words seem to just be adding an unnecessary layer to please emotional needs. If space-time doesn't exist, how can two objects share the same space? Only if they are at two different times. Can the rope break?
A lot of questions there. Let's go one by one. The first one, go with the first one again. Could you repeat that first part?
So the first one is there an advantage in using words over math? Because you are often criticizing math, but you are using your own English Shakespearean maths here.
Oh, no. Okay, let me clarify that. Yeah, math deals with quantities, with numbers, and physics deals with qualitative aspects and with mechanisms. So there is a difference between saying, well, what if we just do numbers? Well, then all you're doing is describing. You're not explaining. An explanation is a little different than a description. That's the first answer to the first question. What was the second question there?
The second question is about objects being at the same place at different times. How is it allowed, and can two objects be at the same place at the same time?
Two objects cannot be at, first of all objects are in the present. There's no such thing as the past. There's no such thing as the future, like in general relativity. Every object simply exists. Exist is not a verb. Exist is an adjective. What we're saying is simply it has location with respect to other objects, and that's in the present. It's in a cross-section of time, you can say, any cross-section of time, if you can visualize that. In other words, we take a single slice of so-called space-time, and that's what exists at that point. Therefore, two objects cannot be at two separate time periods. They're all in the same time period. Every atom is in the universe is a single cross-section of time. Now, can two objects be at the same place at the same time? No, not under the rope model. And I'm talking about atoms. Okay, so two atoms cannot be at the same place at the same time as in quantum mechanics. Even worse, two atoms cannot be, or one atom cannot be at two places at the same time, which is also what quantum mechanics says. They call it, what is it? Forgot the word again.
I think I've heard this, the Pauli exclusion principle. I think it was the Pauli exclusion principle.
Yeah, but that, again, that was derived from having electrons in the same orbit. In other words, it comes from the analysis of the atom, but then they extrapolated that to all particles. And they say, because they can't see these particles, that's why we don't have any pictures of any of the particles in the quantum model. You get a standard model, you won't find a single particle. All you find is descriptions like so much mass, so much energy, you know, that kind of stuff. But you will not find a picture. And why? Because they've never seen a single particle. These are assumptions, and people think that particles have been proven, and they have not been proven. It's just an assumption that the universe is run by particles. And when you put the rope model, obviously it clashes against, you know, the notion that there are discrete particles. Everything's united. All atoms are interconnected.
All right, one last question. Base Devolver says, in a past interview, Bill said that there will be no new technology and that the cell phone is peak technology for our species. Does he still have this view?
Cell phone is not an invention. The last invention was the computer. That was what, 1980s. I worked on that kind of stuff. You know, I did a lot of work on chips and so on. After that, everything was simply a mixture of different inventions. In other words, what is a cell phone? A cell phone is a television, a computer, a phone, and who knows what else, all in one, and portable. You know, that's what we wanted. That's what we always wanted. I mean, if the Neanderthals would have had that, they would have loved it. You know, they say, oh, now I can talk to the other guy in the other cave and so on, right? So that is the ultimate invention, but it's not an invention. It's just what they did was incorporate all these inventions that we already had. We already had the telephone, we had the TV, we had the computer. They said, how can we put that all into one? And that took us, about 40 years, and now we have it. And that's, I think, maybe one of the last really important, not inventions, they're developments that they make of inventions. They simply put them together. You know, these are not inventions.
All right, Bill, it was a great pleasure talking to you. I have some solo subject news to do, so I will say goodbye to you, and let's talk again in the future.
Did you say goodbye or good riddance?
Continue planning your subversion of science in solo, and we'll have you again to continue to combat the mainstream position of physics.
Yeah, we'll see you.
Bye-bye. Oh God, Bill Gaede, you know, I would like to help him. I would like him to accept that there are some things in physics that are valid, but there's no getting into Bill Gates' brain. He only goes by the rope. There's no way to take him out of it. But neutron